Hello, this is Jose Luis and welcome to another hands-on exercise in the series Introduction to Parametric Modeling. This one is going to be very similar as a continuation to the previous video where we did a Vierendeel truss. In this one, we're going to do a Pratt truss, which kind of looks something like that you're seeing here. And as well, we're going to work with two points that are going to be the beginning and the end of the supports, and we're going to be able to control how many spans the truss has and the factor of the depth in relation to the length. This exercise is going to be a little more involved because, as you can see, the relations between the nodes and how we join them with bars is going to be a little trickier. So it's going to involve a little more list manipulation. So we're going to learn a few tricks that are going to be super useful and how to parameterize the relations between elements. We're going to do a lot of sketchboarding for that, actually. It's going to be great. And as a bonus, I'm actually going to show you how to extend this logic to work not just from two input nodes, but actually from a collection of input supports that come from a sample from a process of subdivision of two input curves. So that if we plug those into the definition, we can generate this parametric generative algorithmic modeling that just generates truss beams between two collections of points. And this could become the basis of some kind of like super empowered form of generating structures in 3D. I don't know. I think it's going to be really cool. So if you're interested, then let's get hands-on. Let's get dirty and do some parametric structures. Woohoo! Wonderful. Let's get started. So the first thing I want to say is that I'm actually not sure if what we're going to do is a Pratt truss or a Howe truss, because it turns out that the main difference between the two is whether if the diagonals work in tension, which is the case of the Pratt truss, or whether if the diagonals work in compression, which is the case of the Howe truss. But that is the case if you draw the truss like this, as if it was a bridge, but we're actually going to draw it upside down, as if it was supporting some kind of flat roof or like some kind of long span on top of it. And if we flip it, the behavior of the diagonals is going to change. Here, they're going to become in compression, and here they will become in tension. So I guess the most technical right way of saying this would be that we're going to do an inverted Howe truss, but I'm actually not sure if that is even a thing. So whatever, I'm just going to call it Pratt truss because the way we're going to design it is that the bars are going to be in tension, which is, I believe, the spirit of this particular arrangement here, even though it's going to be flipped upside down. So, and then as in the previous video where we did the Vierendeel truss, what we're going to do is we're going to work with a very similar set of inputs. We're going to assume that we have 2 points somewhere in Rhino or that are coming from our architectural design, whatever, which are the supports, which is where the truss needs to anchor. And then our task is to generate parametrically this shape here, which is going to be, you see that the Howe truss upside down, where each one of the diagonals is going to be working in tension. The things that we will want to control are going to be very similar to the previous exercise. We will want to control the length, but not directly as a number, but just implicitly as the dimension between the two starting and end supports, which are the ones that we're actually going to control. So we're going to control the length only implicitly as we move the points around in 3D space. We will want to control the amount of spans that we have. And for this one, just to make it a little easier, we're going to force that the number of spans is going to be even so that we don't have to deal with the special case of odd spans, and therefore what happens with the middle span. Which way does the diagonal go? Or if we make a cross, which could also be a situation. And then we will control also the depth of the truss. And as in the previous example, we're not going to control it directly with a parameter, with a number, but we're going to control it with a factor. So the depth is always going to be a factor of the length, so 1/10 of the length, 1/12 of the length, 1/16 of the length, which is very commonly how it's done, how how elements are pre-dimensioned in structures. And also, this way, if we make the span between the supports larger or bigger, the depth will also adapt dynamically, which I think is also really nice. So we're going to do that, we're going to control that. And then roughly, the process that we will need to follow is we will first need to create a set of points between the two supports that corresponds to how many spans we have. And then we will need to set another collection of points underneath without the extreme ones, so that, and those are the points on the bottom of the truss. And then, as you can already see coming, we will need to do a little bit of data manipulation to make sure that we join the right collections of points with the right collections of points. So how do we do the vertical chords? So the top chords, the bottom chords, the vertical bars, and then how do we do the diagonals? So it's going to be like 5 families of bars, if you will, because remember, because we are thinking of designing this as part of our structural engineering work, we're going to imagine we're structural engineers here, because this model will go to a hypothetical structural and calculation software. What we will need is the single lines. We don't really care about surfaces or the volume of these things, but we will need individual lines between each one of the nodes. So having one continuous line between the two supports will not work for this particular exercise. If you want to learn more about why that's important, make sure you check our previous video, our previous exercise in this series, the Vierendeel truss. So before we get into the nitty-gritties of list manipulation, let's just get started with the simple thing, which is creating the parameters and creating all the points on the top and the points at the bottom. And then we'll come back and keep some thinking to how are we going to organize and move things around to create the different families of bars that will be in this truss. We're going to start the exercise in a very similar way that we started the previous one, the Vierendeel truss. And if you remember, I created 2 physical points in Rhino that I brought in here as using point empty containers. And then I created a line between them. I subdivided the line in a particular amount of spans that I can control. And just slightly differently than from the previous exercise, what I'm going to do in this one is that I'm going to make sure that the number of spans is forced to be an even number. So I'm going to right click on the slider, I'm going to edit it, and I'm going to click here on even numbers. And therefore, now the next one has to be 8, 10, etc. So I make sure that there is no uneven amount, there is no one central span, just to make things a little easier on my end. And then if you remember also, in order to calculate the depth of the beam, what we did was we took the line, we calculated its length with the curve length component, and let me just please add here a bifocals. And then after that, we created an expression to calculate the depth of the beam as to the depth of the beam like this. So this depth is going to be equal to the length of the curve divided by a factor. A factor that for us was going to be a parameter. So for example, 1/10 of the length of the beam. All right, wonderful. That's great. So we have this. And then if you remember what I did before was in the previous exercise was I moved all the points on the top by a negative z vector that was multiplied by the depth. So therefore, I could create like a second collection of points, the bottom node for the beam. However, in this case, we will follow a similar approach, but we will need to do a little bit of pre-manipulation of the data. Because in this case, what we want to do is not really to take all the points, that are in the, we don't want to take all the points. What we want to do is we want to take only these points here. And those are the ones that we want to move all the way down here. So we're already going to have to do a little bit of data manipulation, which is going to be to take a subset of the points on the top, which is going to start with the second element, and it's going to go all the way until the second to last element. The way we're going to do that is as we learned on the previous videos when we talked about lists, there's a component that is called Sublist which extracts a subset from a list. And what we can do there is we can say that subset that we want to extract is going to be what? Let's think about this. So let's think about this. So if we have our points and the points are labeled 0, 1, 2, 3, 4, 5, and 6, this is how the numbers are going to be labeled for a situation where n, the number of spans, equals 6. So what we need to do is we need to extract these points here. And the way we extract those points is by creating a domain where we say, can you give me, from the original list that goes from 0 to 6, can you give me elements that go from 1 to 5, or in parametric way, can you give me a subset that goes from 1 to however many spans do we have minus 1 unit? And therefore, those will be the elements that will be retrieved, and therefore we will create that sublist. Can we do that? I think we can do that. So let's take the list. We need to say what is the domain of indices to copy. So that's going to be, I'm going to create a new domain. I'm going to construct a domain here, and the domain is going to go from 1, which is always going to be the same, and that's why I'm hard coding it into a panel. I don't want a slider, because if somebody touches that slider, they're going to mess with my definition. And then B will have to be the amount of spans that we have minus 1. So what I can do is I can do either a tiny expression or I can do a subtraction. So I'm going to do a little expression because you know me already. I like this better and it looks more elegant, like x minus 1. It's easier to read. It's not so bulky. And then I'm going to take this here. I'm going to plug this in here. And you can see that now my domain is going from 1 to 5. Okay? So I'm going to move that here. I'm going to move that here. And then what I'm going to do is I'm going to plug all the points in here. And I'm going to see if these points are the ones that I want. You can see that as I turn them on, these points here, from the second to last, they light up. And if I modify the number of spans, everything is still parametrically, that looks good. So I think this is the sub collection that I want to move to the bottom. So therefore, I'm going to use this here. And now I'm going to turn this on. And you can see that now I have the collection of points that are all the points from the top minus the first one and the last one. And then those copied on the bottom side. So great. So this is looking great. So, but as you saw on my previous video, because things are going to get a little complicated very soon, I want to make sure that I have a very clear sense of which points are which. So for the sake of clarity, before I start manipulating them, I'm going to, and this is really good practice to keep things tidy, so I'm going to just pass all these points through an empty point container box, and I'm going to label it. I'm going to say top nodes, and here I'm going to, in parentheses, I'm going to write all to make sure that we know that these are all the points. Then I'm going to write and not copy paste this one, and then I'm going to say top nodes, but here I'm going to write minus first and last. All right, and then the last is, this is going to be bottom nodes. And here I'm going to say all because I don't really need to differentiate between minus first and last. There was no such a thing here. Okay, so now I have here the result of my first processing, like source nodes. And this will be the one that I will use to start modifying and adding and removing, etc., to do the data matching, which is going to be, and I'm going to turn off the line here as well. And just for the sake of clarity and see things very clearly as well, this is very, very good practice when you're doing data matching operations. I'm going to keep here one of these components that gives me the numbers of elements on the screen. And what I'm going to do is I'm going to make sure these are all the nodes. Yes, these are all the nodes except for the first and the last. And these ones are all the ones in the bottom. So I think this is looking good so far. So I think we are ready now. We are in a pretty good position to now start looking at which kinds of which families of bars are we going to create and how we're going to match them together. The first family of bars that we're going to create, I think, is going to be the easiest one, the low-hanging fruit, which is going to be the vertical bars. And it's going to be the vertical bars because if you think about it, we already have a group of points that are all the top nodes, except for the first one and the last one. We already generated that collection before. And we also have another collection, which is basically all the nodes in the bottom. So if we match those one to one, we're going to get all the vertical bars right away. So it's going to be pretty straightforward. So that is just going to be as simple as, where are the top nodes minus the first and the last one? It's these ones. So, and then the other collection is this one here. So we're going to do simple line between two nodes. So that's going to be between the top and between the bottom nodes. And voila, we have all the vertical nodes. So that was pretty straightforward. And just because I really, really want to be very methodic about this, I'm going to turn this one off. And I'm going to write here vertical, I want caps. Where are my caps? Vertical bars. And that's going to be this one here. Okay, so we got this, and this is going to be vertical bars. Correct. So we got that. What are the next ones? Which are the next ones that we're going to do? The next family of bars that we're going to generate are going to be the top chords. And they're going to be the top chords because we already discussed in the previous video how, in order to do this, one of the easiest ways is going to be if we have a collection that is all the points, all the nodes on the top of the bar, what we can do is we can generate two collections. We can generate a collection that is going to be all the points minus the last one. So those are going to be all the initial points of the lines. And then we can generate another list, which is going to be all the original top nodes minus the first one. And this all will be the end point of the bars. And then you can see how by doing that, it's very simple to see that if we join now with a line component element number 0 from the first list with element number 0 from the second list, we will get this bar. If we join element number 1 of the first list with element number 1 with the second list, we get this bar, and so on and so on and so on. We saw that on the previous video, and the way we're going to do this in this video is going to be slightly different, because what we did in the last one is that we took a subset. So we took a subset, we took all the points, so all the top nodes, and then what we did was we created sublists that we splitted the list, starting with the first element and starting with the last element. So for this one, I'm going to follow a slightly different technique that is going to be a little faster, if you will, which is going to be shifting the lists. So let me show you how this looks. So right now I have all the points in my collection. So that's going to be this one here. And then what I would like to do is now, instead of splitting the list and just retrieving all the elements minus the first one and all the elements minus the last one, I'm going to shift the list. Shifting the list, if you remember, means offsetting all the elements. Okay? So what I'm going to do here is I'm going to take the list, and then the offset factor, for example, is going to be the value of 1. And by doing that, I'm going to end up with a collection of points, a collection of points that is going to be all the points except for the first one, which I actually still have it in my collection. So, and this is because if you remember from my previous video, I said that the wrap input, if it is set to true, it will take the last elements and then it will put it back at the beginning. So what I actually want to do in this case is to set that to false. So I'm actually going to write here on a panel false. and I'm going to set that here. And if I do that, then because elements don't wrap, as all the elements get shifted in the list, the one that was the last one cannot shift a position forward, so it just gets dropped. It basically disappears. So now I have a list that is shifted, and this will correspond to the collection that I have marked in red. So all the points on the top of the truss minus the first one. And then what I would like to do is I would like to make a very similar thing. So I'm going to copy paste this, and instead of 1, I'm going to type here -1. And then I'm going to now plot those. And you can see that because I also have wrapping deactivated, you can see that I have offset all the elements 1 position to the left, and therefore this point that was here moves here, and now the one that was in the first, it doesn't wrap, so it just disappears. So with this, so now I have the collection of points that are all the points minus the last, and I have another collection which is all the points minus the first. If I join this with a line between 2 points component, you can see that I will now have, let me just plug a panel here to make sure that things are working well. I have a list that is going to be, let me do 6 spans here so that it's a little easier. If it's 6 spans, I should be getting 6 lines there, correct? And I can see that I am getting 6 lines and each one of them has the exact same length. So that is correct. That sounds really good to me. Just to make sure that things are working well, again, what I'm going to do is I'm going to actually bake this result. So I'm going to bake this, I'm going to close Grasshopper, and you can see that I have what looks like a continuous line. But if I click on it, you can see that they're actually segments of lines one after the other, which is exactly the result that I want. So this is looking really good. So I think things are working fine so far. Remember, because I like things super tidy and clear, and this is really good practice because trust me, Grasshopper definitions, they go nuts very soon with complexity. So I'm just going to make sure that I write here top chords, and I'm going to all caps that top chords. All right, beautiful. I'm going to wrap this into, no, I didn't want that here. So I'm going to wrap this here, so, oops, and I'm going to give it a name, so top chords, all right? And then for the ones on the bottom, I'm going to do the exact same process that I just did, but instead of drawing from the collection that had the top elements, I'm just going to draw from the collection that had the bottom nodes. So literally, it's going to be as simple as just copy pasting this whole block here. All right. And then let me remove these 2 components from here. But instead of drawing from the top nodes, I'm going to draw from the bottom nodes. So I'm just going to plug this in here, and I'm going to plug this in here. And then you can see that the first list is going to be all the elements minus the last one. The second list is going to be all the elements minus the first one. And then when I join those with lines, I get these 4 lines, hopefully. Yes, 4 lines with equal length. All right. So, but then let me rename this because copy pasting is the devil, remember? So bottom chords, and here I'm going to write bottom chords. Beautiful. So again, remember shift list. What does is it offsets all the elements 1 position, but a byproduct of, or a side effect of this operation is that if you set wrapping to false, all the elements that become empty with this repositioning disappear. They do not go back to the beginning of the list, or they do not go back to the end of the list. And therefore, implicitly, it's a way of also removing elements from a list, which I find a little bit more elegant than the whole splitting ordeal. It's a little easier for me to read. I don't know. It's a different approach. So wonderful. So what is next? We just have to do the diagonals, right? How are we going to do that? For the diagonals, as you can probably start imagining, we cannot actually do all the diagonals at once, because since we have two orientations, the left ones and the right ones, and they kind of have slightly different logics, we will just have to do two separate processes, one to fetch the ones on the left and another one to fetch one on the right. And you probably see where I'm going with this. If what I want to do is I want to take the diagonals that are on the left, what I will need to do is from all the lists of all the points that I have in my truss, I would need to do some list manipulation so that I isolate the first three nodes on all the top nodes, and then the first three ones on the bottom. All right, for in this particular case of a beam with 6 spans. So I will probably want to use some kind of operation where I extract a subdomain from the lists of original nodes. And what will be the logic here? So if I want to say, for example, I want to take from the top collection, what I would like to do is I would like to take all these points here. What that means is that I would need to create a domain that starts at 0 and that ends at 2. So that is for my extraction of those points. But 0 can be a hard-coded number because it's always going to be the beginning of the domain. But 2 has to be a parametric number, or a number that depends on how many spans do we have. And what do we think the rule is going to be? The rule for the number 2 based on a number of 6 spans could probably be something like this. We can see that the number 2 might be 6, the number of spans, divided by 2, and this can be hard-coded, minus the value of 1. Because this is 3, right? So we could write a rule where the domain that we choose to isolate the first elements that we're going to do for the diagonals could be something like this. The domain could be the value that goes from 0 to the number of spans divided by 2 minus 1. And this could be an inclusive domain that is typically done with brackets, okay? And then what about the other family, the family of blue points that I have in the diagram? How could we do that? The domain would be, for this case, it would be pretty much exactly the same, because we also want numbers that go from 0 to the number of spans divided by 2 minus 1. So the way we're going to do this is just going to be as easy as taking from the original collections, extracting subdomains that go from 0 to this parametric number, the number of spans divided by 2 minus 1. Let's take a look at how to do that. So we're going to go back to Grasshopper, and then we say, all right, we have all the points, all the nodes on the top, so all of them. So let me create a sublist here from all these top nodes, but let me before create a domain. So I'm going to construct a domain, and the domain is going to go, as I said, from 0, which is going to be a hard-coded number, and that's why I'm going to use a panel, because remember, I don't want a slider there. I don't want anybody by mistake to change that. And then B is going to be this parametric number, which is in relation to how many spans do we have. So obviously, you see where I'm going with this. I'm going to create an expression. I'm going to remove the first element, and I'm going to name this n, as in number of spans, for example. And this is going to be the number of spans divided by 2 minus 1. And I think the parentheses here are redundant. I don't think I need them, but I think they don't really hurt. It's just visual flavor. So I'm going to plug this in here, and the result for this one is going to be 2, which is great. And then I'm plugging this here, and then you can see that what I have isolated in this case are the first 3 points of the top list. And to make sure that this works, let me change the number of spans. And you can see that as we grow, we always get the first half, except for the point in the middle, which is great. So I think this is working pretty well. So at this point, I think we can take the points on the top, So are going to be these ones here. This is the domain. And the points in the bottom are going to be a sublist. So I'm going to copy and paste this with the same exact domain, but instead of drawing from all the types, all the points, all the nodes on the top, they're going to draw from all the nodes on the bottom. So I'm going to plug that in here. I'm going to visualize this. So I'm going to plug this in here, and these two look good here. And then I think at this point I can do line between 2 points, and ta-da! It works! Beautiful. And just making sure here. So I'm going to plug this in here, and I'm going to say left diagonals. Sorry. So I'm going to do left diagonals. Ah, so left diagonals here. And I'm going to group this, the diagonals left. Okie dokie. So I think we got this working. And if I increase the number of spans or not, everything looks to be working, right? Okay, so that is working well. Now, what about the other diagonals? The right-hand side diagonals are going to need a tiny bit more of arithmetic, just like a little bit of more of adding and subtracting numbers. Because if you look at them, if you look at these diagonals, what you will see is that what we need to do is we need to extract the last half, more or less, of the points on each one of the collections, the one on the top and the ones on the bottom. And you're going to see that their index numbers are a little bit more all over the place. So let's take a look at, for example, what would be the rule for the points that are on the top. So you can see that the domain that we would need to construct here would be something like, for example, this would be the number of spans. So this can be n directly. And then this one here, as what we saw before, is that in order to find this one, what we did was we realized that this number was always going to be half of this one. So that's this one minus 1, correct? So this one was always going to be n minus 1. Sorry, it was going to be n divided by 2, which is this one. And this one will be n divided by 2 minus 1. So I guess in this case, for this one, what we can do is that 4 is going to be n divided by 2 plus 1. Does this make sense? So the rule for the domain that we're going to create is that the first value is going to start at n divided by 2. That will be this number. Plus 1, so that will be this one. And then it's going to go to n, which is the number of spans that we have. Correct? So this is the parametric rule of the index numbers of these points here. So we're going to try that. And then the other one, how is the other one going to work? Well, let me undo this. Yes, so we have this one here. So what about, let me turn that off. So what about this domain here? So this is going to be also a little bit more arithmetic, because we know, for example, that this number here, which right now is 4, is kind of the last value of the list of all the elements in the bottom nodes. And because basically the bottom nodes are the same amount as the top ones, minus the beginning and the end ones, if this value is always going to be n, turns out that this value will always be n minus 2. So if this is 6, this is 4. If this is 10, this is 8. If this is 3 million, then this is 3 million minus 2. Correct? So that relation holds, and therefore we can know that this number is also always going to be n minus 2. And then I think that geometrically, because the number of spans are even, it actually follows that this number, the one in the middle, will always be n minus 2, so this same value, divided by 2. It's always going to be the half of whatever this one is. So if that's the case, then I think we can make a rule here where we say that the domain for the points on the bottom is going to be n minus 2. So that's going to be this point here, and then n minus 2 divided by 2. So half of that is going to be that one here. And therefore, these are going to be both of our rules for designing the domains that we're going to use to extract points from the list of nodes on the top and the list of nodes on the bottom. Okay, so and I see Hania, who is live on the chat as I am recording this tutorial, is suggesting that another technique could be to do the exact same thing that we did for these ones. But before, what we do is we reverse the whole list. So we reverse the points on the top and the points on the bottom. So we reverse two lists, and we do the exact same technique that we used for the previous ones. That is also a technique that works. Perhaps it's a little less elegant or a little less clean because it involves reversing and then doing. It's so a little less straightforward, but it would also work. It would do the trick. And for such simple geometry, it's not going to be a big of an overhead. I like this approach better because it's a little cleaner, but also it gives me the opportunity to break down with you some of the numerical logics of how the points are sorted inside of this let me say that, please, inside of these lists of points. So I think it's good practice, okay? But yes, so reversing the list and using the same technique as before would also work. Nevertheless, let's take a look at how would we implement this approach. Let's do this. So I'm going to go back to my definition, and then I'm going to use sublist to extract these two smaller collection of points from the original ones. So I'm going to sublist from the top nodes here, and I'm going to copy and paste another one, and I'm going to sublist from the bottom ones, and I'm going to take these two components and bring them all the way down here to work with them a little cleaner. So these would be the ones on the top, and these are going to be the ones in the bottom. Now, I need to construct a domain and now these are going to be different domains for each one of them. So for the one on the top, as we saw in the diagram, the rules are going to be that I'm going to use n divided by 2 plus 1. So what I'm going to do here is the beginning of the domain, I'm going to copy this, and the beginning of the domain is going to be n divided by 2 plus 1, as we saw on the diagram. Okay, and then the other end is going to be n, which means the amount of spans that we have. That is a parameter that we have in our definition. So I'm just going to draw here from this slider, which is the one that has the amount of spans that we have. So our domain is now from 5 to 8. And then if I plug this in here, you can see that I am getting the 4 elements that are by the end of the list. And you can see that if I expand, this is kind of working, it's doing what I expected, so that's great. And so that is working so far. And then I'm going to construct for the ones on the bottom another domain. All right, so I'm going to construct another domain. And as per the rules that we defined before, we said that the end of the domain is going to be the amount of spans minus 2. So I'm going to do that. I'm going to copy this expression here, and I'm going to say this is going to be the amount of spans divided by 2. That's going to be the end of the domain. And the beginning of the domain was that same value divided by 2. So I'm going to go back here, copy and paste this, and say n divided by 2. Sorry, no. Oh, wait. I'm not doing this right. Sorry. It's n minus 2. And then n minus 2 divided by 2. Sorry. I was confusing myself. So I was a little confused. So this is n minus 2. Apologies for the confusion. And then this is why doing sketches is so good. And then this is going to be n minus 2, and all of this, and now I do actually need the parentheses for real, is going to be divided by 2. And this again is another one of the reasons why I like the expression component. Imagine having to do all of this and this and this with regular mathematic components is very tedious. It would have been a lot of visual clutter. So this should be the two domains, the domain, and then the sublist, and then it just gives me these points here. And then I can just extract this and increase this, and I think this is working. And all right, are we ready for this? So let's do a line between 2 points, and then the first point is going to be the top ones, the second ones, and boom, and this is working. Yoo-hoo! And because I'm a little OCD, I'm going to do diagonals on the right, and then I'm going to group all of this, and I'm going to say this is the diagonals on the right, and boom, and I think I have my full truss working, right? So let me see. If I move the point, the whole thing becomes smaller. If I change the factor, the Pratt Truss goes up and down. And if I change the amount of spans, I got more or less, or more or less. Yoo-hoo! Boom, boom, boom! It's working! Yay! Before we do anything else, something that I would like to remind all of us is that the nice thing about this parametric definition for a truss is that each one of the elements is individual. So what I can do is, and also for the sake of making things a little clean, I can create a final empty box. For example, a line empty box where I aggregate all together with the shift. I aggregate all the bars that I have generated, and this is kind of my main output. So this is like my my main, what is it called? This is kind of like my main my whole Pratt truss. All right, and then what I can do is, like, for example, I can bake this, and let me say that I'm going to group it so that all the bars are grouped. So now I can close Grasshopper, and you can see that I have my truss that I could send it. I can actually move it around and send it anywhere to my structural analysis software. I can even ungroup it, and then as I ungroup, you can see that I can select all the individual members, including the top ones, which are in between nodes, and the bottom ones, which is kind of quite clean and quite nice. So this will be the main output of my definition. And just like I typically like having like a big box that says these are the inputs, I typically like having a big box that says this is the outputs. And sometimes what I even do personally is I bring it all the way here. And maybe what I do is, like, I right click and I say wire displays. I want hidden. I don't want to see anything unless I click. And this is my output. This is the main result of my definition, because at the end of the day, when people use definition, they should not care about what the code is. The only thing that they should care is about what are the inputs, what things do they touch, and what is the main result of an algorithmic parametric modeling process. So that's one thing. Another thing that I would like to highlight is, because now we have an algorithmic rule to generate these trusses, we can actually make it a little nicer and fancier, because since we start from 2 points, one at each end, and then everything that comes afterwards draws from that relation between those 2 points, then it turns out that it doesn't have to be just individual single points for support. Let me show you a trick. So for example, let's say that I had some kind of free form something, like for example, like a floor structure or whatever, and then I wanted to create like a series of parametric trusses between them. So for example, something like this. All right. What I can do is I can bring the 2 curves into, nope, not that one, the 2 curves into Grasshopper, so one here, and then I'm going to set the second one. It's going to be here. I'm going to subdivide each one of them in a set amount of points. So for example, that's going to be 20 subdivisions, if you will. And then I'm going to copy and paste this. And then here I have a collection of input points, and here I have a collection of output points. So if instead of using one single support and one end support, I use a collection of start supports and a collection of end supports, two lists, you can see that all of a sudden I get this parametric definition that generates Pratt beams between two collections of points. All right. However, if we look closely enough, let's reduce the number of these elements. If we look closely enough, we can see that there's something not right going on. So you see how these dimensions are not actually, and the more we add, we get some kind of strange curvature going on, but at the same time, we also get this collection of added points here. So something is not working very clean here. And as I typically say, when things are not working exactly the way we want, what do we think could be the problem? Well, of course, the problem is probably going to be related to data. I'm not going to get into the whys, but it turns out that that the problem is because we are outputting lists here of points. Those lists get messed up when down the stream we do list manipulation. So if instead of that, what we did was we grafted each one of the outputs, because now each of the points is in its own branch and it becomes its own list, then the problem gets solved. And now we get this parametric definition with trusses that are covering the span between the two. And one of the beautiful things as well is that because we decided to do the depth, do it in a way that was proportional to how far off the nodes are, then the depths are not the same for each truss. They are different, and they are in a way a little more optimized. They're a little more optimized because you only need a smaller depths for the elements that are closer to each other. You can see how here the depth is very much, whereas here the depth is much smaller. So it's a very interesting way of creating parametric definitions. And it's a very interesting way of creating parametric structures. And I could add some pipes here and make it look a bit more nice, but it may take a little bit of time, and it's going to take some time, and it also is going to slow down my computer because representing pipes is actually quite expensive. So yeah, so I'm not going to do that. So beautiful. So that was it. That was it. That was a parametric definition to create Pratt trusses between two supports or between two collections of supports. And I think that's it for this exercise. So just because I think lists are super, super, super important, I'm still going to do another exercise where we're going to do Warren trusses, which is also going to be very similar, but more list manipulation. If you think you're good with what you saw, you're welcome to skip to the next few exercises. Otherwise, I really, really recommend that you still check all the ones that are going to be related to lists, because lists are super important. List manipulation is super important, and it's always a topic that requires practice to get our heads around, to wrap our heads around it if it's the first time that we're doing this kind of computational operations. So see you on the next video. This was Jose Luis. This was Introduction to Parametric Modeling. And if you are liking what you're seeing, maybe like this video, maybe subscribe to the channel, maybe turn on notifications, maybe leave a nice comment, or maybe just post some links to some work that you're doing from what you're learning on this list. That would be great. Thank you very much, and see you on the next video.